Good morning, everyone. My apologies for those of you that attended in person this morning. We had audio-visual problems, so I'm recording today's lecture electronically, and you're obviously here watching it on YouTube. So just a reminder about where we are and where we're going. The undergraduates, you're starting in on assignment 3 this morning. Graduate students, you're starting in on assignments 5 and 6. I just wanted to say a few things about assignment 3 for the undergraduates. In assignment 3, you're going to be implementing sensors for your robot. You're going to be introduced to for many of you, two new Python packages today in this assignment. The first one is NumPy, which stands for Numerical Python. This is a very useful Python package to know, so please familiarize yourself with NumPy if you haven't used it before. And you're also going to be making use of matplotlib, which is a visualization Python package. Again, very popular, very used for a lot of different things, a good Python package to know. Okay, and for the graduate students, you're implementing assignments 5 and 6. Assignment 5, you're going to be refactoring your code and making it more object-oriented. To make it more object-oriented, this takes a fair bit of time and effort, so please set aside enough time for assignment 5 and assignment 6 this week. Okay, back to the lecture material. We started in last time on the tools of the trade, and specifically we were talking about artificial neural networks. You are going to be implementing an artificial neural network in this class, which takes input from the robot sensors and transforms those sensor values in some way to produce outputs. And we started by talking about exactly that last time, which is how neural networks can actually encode arbitrary functions that transform their inputs into outputs in some way. We looked last time at building up a simple neural network like you see on the left that computes a relatively simple function like logical OR. In this case, we want a neural network that when both inputs are 1, it outputs a 1, and in all the 3 other cases, it outputs a 0. We saw a way to do that. We then finished last time by looking at how to alter our neural network so that it computes the logical function OR. We ended by talking about exclusive OR, in which exclusive OR in the 4 cases, we want our output bit to be 1 only when exactly one of the inputs is 1 and the other input is 0. So this is a non-linear function. And it turns out that there is no set of synaptic weights and a threshold for the threshold activation function associated with the output neuron that will actually encode the exclusive OR function. In order to create a neural network that can embody this particular function, this particular way of transforming inputs into outputs, is to change the cognitive architecture of our neural network. As you can see here, we still have our 2 input neurons and our 1 output neuron, but we have added 2 neurons in between. We have connected both inputs to the first neuron and both inputs to the second neuron, and then these 2 intermediate neurons are connected by a 5th and 6th synapse to the output. We have our input neurons up here, our output neurons down here. The neurons in the middle here are known as hidden neurons. They're known as hidden neurons because they're kind of hidden from the outside world. They only indirectly have an influence on the outside world. They're not directly receiving input from the outside world, and they're not directly supplying output to the external world. They're hidden or buffered from the outside world in some way. So it turns out that this neural network is large enough and complex enough to be able to encode the exclusive OR function. In order to do so, we need to come up with weights for these 6 synapses. And also, as shown in the brackets here, we need to determine thresholds for the activation functions associated with the hidden neurons and the output neurons. You'll notice in this case that our input neurons have no activation functions, but the hidden and output neurons do. The input neurons have no activation functions because they're just receiving numbers from the outside world. Okay, so it's difficult to look at this and immediately determine what these 6 synaptic weights and these 3 thresholds should be, but you might be able to build up an intuition for how to encode the exclusive OR into this neural network by noticing that we can use these 2 hidden neurons to compute subfunctions and then combine the results of those 2 subfunctions at the output neuron. If you have a look at the truth table on the right here of the exclusive OR, you'll notice that exclusive OR looks a lot like OR, except it differs in the 4th case. Yeah? So the intuition here is we can use one hidden neuron to compute the OR function and pass that along to the output function. We can compute a function over here at the second hidden neuron that computes another function and suppresses the 4th case. So in the one case, in the OR case, we would want a 1 here, but in the exclusive OR, in this 4th case, we want it to output a 0. If we have a look at the AND function, we can see that the AND outputs a 1 in the 4th case. So the intuition here is that if we compute the OR function at the first hidden neuron and then compute the AND function at the second hidden neuron, the second hidden neuron will only light up in the 4th case because it's computing AND. And if we turn this synapse into an inhibitory synapse, it will suppress what's coming from the OR function in that case, which is the 1, 1, it's trying to output a 1. So here we go. We've already done this. We're creating an OR function over here. So we assign a weight of 0.5 and 0.5 to the synapses arriving at this neuron. And we set its activation threshold to be 0.4 below these weights. So this output neuron will light up when one or both of the inputs is a 1. And we encode the AND function over here. So we set the weights to the 2 incoming synapses for this neuron also to 0.5, but we set its threshold to be higher so that this output neuron will only fire when both inputs are set to 1. We then set this synapse to have a weight of 1. So it's simply the value that arrives here, the result of the OR function gets passed down here to the output neuron. And we set this particular weight to be negative. So remember, this is computing the AND function. So only in the 4th case is this a 1. And when it's a 1, that lights up and it actively inhibits the output neuron here. So let's work our way through this example here. In this case, we're setting just one of the 2 inputs to a 1. 0 and 1 for the OR case flows down. So we have a 1 here. 0 and 1, if this is computing the AND function, this is a 0. So at this point, we have a 1 over here and a 0 over here. 1 times 1 plus 0 times minus 1 is 1, which is higher than 0.5. And the output is set to 1. And we get the correct result for the exclusive OR function. If we now think about the 4th case, we take the 2 inputs and supply them up here. So now we have 1, 1 over here. We know that OR results in a 1 over here, and the AND function results in a 1 over here as well. 1 times 1 plus 1 times minus 1 is 1 plus minus 1, cancel each other out, and we get a 0 arriving at the output neuron here, which is below the activation threshold, which sets the output to 0. Okay. This is probably something that's best done by yourself in pen and paper. What I want you to take away from this is that there are certain transformations that are not possible for simple neural networks, and we need to make larger neural networks to enable those more complex transformations. Why does this matter for us in evolutionary robotics? It matters because when we create our robot, we try and evolve it to perform a task, there may, unbeknownst to us, there may be a particular transformation of the robot's sensations, its perceptions into motor actions that it needs to be able to perform in order to perform whatever the task we want it to do. If that robot has an overly small neural network, the evolutionary algorithm can never find appropriate weights or activation thresholds to get the robot to actually perform that sensor to motor transformation. So one of the things we can do in evolutionary robotics is allow the evolutionary algorithm not just to evolve the synaptic weights or the activation thresholds of the neurons. We can ask the evolutionary algorithm to evolve the cognitive architecture itself. The evolutionary algorithm can add neurons and synapses and then determine whether that enlarged neural network allows the robot to perform whatever it is we want the robot to perform. Okay, just a couple of other items I wanted to mention about neural networks before we move on to evolutionary algorithms. As I mentioned, there's a difference between evolutionary algorithms and learning algorithms. In learning algorithms, we assume that we know what the output neuron values should be. In the case of our robots, we don't know. But if we do know, there's a very, very famous algorithm in machine learning known as the backpropagation of error. And it works as follows. Let's imagine we wanted to create a neural network that computes a much more complicated function. We still have two inputs, but we now have two outputs. And I haven't filled in all the desired outputs here, but assume that we have some ones and zeros in our output columns here. We'd like to create a neural network that embodies this function. If the function's overly complicated, we can't really do it by hand. So we might start by setting all the weights to 1. We don't really know what they should be. We then flow values from the input layer down to the output layer. So at this point, we've supplied the inputs with 0 and 1, and these flow down. And in this particular case, I'm not showing the activation thresholds, but assume that the activation thresholds are set in such a way that the two outputs are 1 and 1, but we wanted the outputs to be 1 and 0. So the first output is correct. The second output is incorrect. We compute the errors at these two output neurons. In the case of the first output neuron, the error is 0. In the case of the second output neuron, the error is 1. And we then take that error and propagate it backwards. We flow backwards from the output to the input, and along the way, we use the error to determine how to change the synapses. So in this case, if we flow backwards, we can change the synapses from 1 to 0, so that now if we flow forward again, we'll get 0 error in both cases. This is the basic algorithm that underlies all modern machine learning, and this is how neural networks learn or are trained in order to perform some desired function for us. The assumption, of course, is that we know what the outputs should be. You'll notice that the backpropagation of error algorithm is causing localized changes to the synaptic weights. So in this example here, not all the synaptic weights changed, just the ones that were causing the error at the second output neuron. By making a small change to a subset of the synaptic weights, we have a low chance of increasing the error for another input pattern here. Yeah. So this is like using tweezers on the neural network to make a slight change only where there's an error. We'll come back to why that's important in a moment. Another big issue with neural networks is known as overfitting. This is something that can come up in evolutionary robotics as well. But I'll just show you a simpler example here. Let's imagine that we had a particular data set represented by the table in the upper right here. Each row here corresponds to a particular patient that's arrived at the emergency ward at the hospital, for example. And upon admittance, each patient is given a series of tests, and they test positive or negative for an K symptoms. These patients then also test positive or negative for a given disease. COVID would obviously be the obvious example to use for this today. It might turn out that there's a particular pattern of symptoms that predicts whether or not the patient has the disease or not. What we would like to be able to do is teach a neural network to learn this pattern so that when the n+1th patient enters the emergency ward and we give them their series of tests and they test positive and negative for a number of symptoms, we can predict whether or not they're suffering from a given disease. Okay, what is the size of the neural network we need to make to train it to possibly learn this pattern? Well, we have K symptoms. So we have K input neurons representing each of the K symptoms, and we have one output neuron, which is going to turn, which when it's set to 1, that's the neural network indicating that it thinks that particular patient has the disease. An output of 0 is the network's prediction that that patient does not have the disease. As we saw in the exclusive OR example, we might want to include some hidden neurons and wire the input neurons up to the hidden neurons and then wire up the hidden neurons to the output neurons. Turns out that if we choose too many hidden neurons and apply the backpropagation of error algorithm, the neural network can actually learn to cheat, and it cheats in the following way. Let's imagine that we have our n patients, and we created at least n hidden neurons. It can cheat in the same way that some of us cheat when we have an exam the next day and we haven't studied enough. We might memorize previous year's exams, hoping that the professor issues that year the same exam that she used the year before. Neural networks do the same thing. It's sometimes easier for them to memorize answers rather than learn underlying patterns. How does this work? Well, it could be that hidden neuron 1 learns to recognize, only lights up when there's the particular subset of symptoms that patient 1 registered. And the weight coming out of that neuron is set to whether or not that patient had the disease or not. The second hidden neuron, the weights of the synapses arriving at that second hidden neuron are set so that the second hidden neuron only lights up when the subset of symptoms for patient 2 arrive at the input layer, and so on. So we basically have n hidden neurons that are being trained to recognize whether it's patient 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or n patients. It recognizes each of the patients. It then memorizes whether or not that patient had the disease or not. Yeah. So if a network is trained in that way, or a network ends up being trained in that way, and we supply obviously the symptoms from patient N, then all the other hidden neurons are 0, and the nth hidden neuron lights up, and it outputs whether or not patient N had the disease. And that neural network can get an error of 0 for all of these patients. The problem, however, is, of course, it hasn't learned the pattern. So if we now present symptoms from patient N+1, the neural network has no idea whether or not patient N+1 has the disease or not. Yeah? This is known as overfitting. It's fit all the data, but has avoided having to learn the underlying pattern of how the symptoms predict the disease or not. Again, how does this relate to robotics? You're going to evolve your robot to perform various tasks. If we then take that robot and put it in a new environment and we want it to perform the same task in that new environment, it may not know how to because it may have memorized sensory, may have learned sensory pattern, may have memorized sensory patterns that it experienced in the old environment, and it's not able then to generalize. It's not able to perform the desired behavior in a new environment. Okay. A couple other things that will also crop up in this course that are relevant. Recurrent connections are a way to add memory to a neural network. What we've seen so far are synapses that are flowing forward, meaning they're flowing from the input layer directly to the output layer, or from the input layer to the hidden layer, and from the hidden layer to the output layer. We can include recurrent connections that add in cycles in the following way. Imagine now we have two sensor neurons and we have two motor neurons. As you can see here, the sensors are connected to the motor neurons, and we've now included a fifth and sixth synapse, which are recurrent connections. We're connecting the motor neuron, motor 1 to motor 2, and motor 2 to motor 1. What happens in this case? Well, let's imagine we take our Bratenberg vehicle and we put it in a virtual world, and in that virtual world at time step t, it registers on its left sensor a sensor value of 0, and on its right sensor it detects a value of 1. I'm not showing you the synaptic weights now, or the threshold activation values. Just assume they're such that this results in a value of 1 arriving at motor neuron 1, and also a value of 1 arriving at motor value 2. If these two values are attached, if these two motor neurons are attached to wheels, then both wheels will spin at 1 radian per second, let's say, for example. So we have our little Bratenberg vehicle. The wheels start spinning and it moves. The moment that the robot moves, there is a sensory repercussion of its action. This is what we talked about when we talked about embodied cognition last time. The minute that it moves, in this cartoon example here, at the very next time step in the simulator, at time t plus 1, both sensor values change. Now the left sensor registers a value of 1 and the right sensor registers a value of 0. We need to compute the value. We need to compute the value first of the first motor neuron here. We see that we have 3 incoming synaptic weights, 3 incoming synapses. So we take this the value here, multiply it by this weight. We take this value, multiply it by this weight. At this second time step, we have not yet computed the value of motor 2. So we use the value of motor 2 from the previous time step, which was 1. So 1 times whatever this weight is, 0 times plus 0 times whatever this weight is, plus 1 times whatever this synaptic weight is, to set the value of motor 1. So you'll see that the new value of motor 1 is actually a combination of current sensation, current sensor values, and past motor actions. So this is the robot's way of remembering or incorporating into its current actions, or its current action being influenced by an experience it had in the past. I just realized I neglected to mention something that happens at the previous time step t. When we're computing the value of motor 1, we're also multiplying this value by this weight plus this value times this weight. At this first time step, there is no value for motor 2. We haven't even computed that yet. We're still working on computing the value of motor 1. So we disregard this particular multiplication here. So motor 1 here is simply 0 times this weight plus 1 times this weight. Yeah? Okay. So why do recurrent connections matter? Again, when you come to evolve your robot for a given task, that task may require the robot to remember stuff from previous time steps or not. If you feel that it might be useful for the robot to remember past information, you can build into your robot's neural network controller recurrent connections. Okay. You'll remember a few minutes ago I mentioned the backpropagation of error, where we assume, in some cases, we assume if we know what the actual output values should be, we can propagate error backwards. Turns out that the backpropagation of error algorithm doesn't work very well for recurrent connections. When you have a neural network with recurrent connections, for the following reason. Let's go back to our cartoon example before. In this example here, when we supply an input of 0 and 1, 0 and 1, we want the network to output 1 and 0, 1 and 0 down here. At this point in time, our network is getting it half right. The first output neuron is correct, but the second output neuron is incorrect. We have to propagate the error at this neuron backwards along all the synapses arriving at this neuron. There are 3 of them, this one, and this one. So we do so, and we make changes to this synapse, and this synapse. As we've traveled backwards, we've now traveled backwards along this synapse to this neuron. We've traveled backwards along this synapse to this neuron, and we've traveled backwards from this synapse over here. And at least when we travel back to this neuron here, we also have to continue propagating things back, because the error might not have been here, here, or here. It might have been somehow coming in to this neuron and then propagating along to this neuron. So we also have to propagate error backwards from this neuron along this connection, and this connection. So I've turned all 6 of these synapses red, because they are potentially being changed here. And you'll notice that we're now potentially making changes to all the synapses in this neural network. In the case of recurrent neural networks, it's hard to isolate where the error was originating, so we end up sort of flowing outward along most or all of the synapses and ending up making global changes to most or all of the synaptic weights. That's like reaching into your laptop and hitting it with a sledgehammer and hoping that makes things better and not worse. Obviously, the chance of that happening is very, very low. So it's very, very difficult to use the backpropagation of error algorithm for recurrent neural networks. Luckily, in this class, we are not using backpropagation. The evolutionary algorithms do not have the same problems with tuning recurrent neural networks. Okay, just to consolidate our discussion about neural networks, we've talked a little bit about supervised learning, which assumes that for every possible combination of inputs, we know what the outputs should be. Evolutionary robotics is not supervised learning. It can be known as a semi-supervised learning problem. For every possible combination of sensations that our robot can perform, we don't know what the motors should do. All we know is that after a given period of time, we know, for example, how far our robot has moved, or how well it's grasped an object, or how well it's lifted an object. So we have a single floating point value, which tells us sort of how well that robot is doing. And we usually use that value to reward the robot in some way. So if the value is high, we reward the robot by allowing it to produce offspring, randomly modified copies of itself. If the value is relatively low, we punish the robot by deleting it, or it's not allowed to produce any offspring. Okay. That completes our discussion of artificial neural networks. Obviously, neural networks is a massive and fascinating subject in and of its own right. We don't have time in this class to go into all the details. I've tried to just touch on some of the aspects of neural networks that'll be relevant for us in this class. Okay. Moving on, we're going to talk about a different tool of the trade now, which is evolutionary algorithms. So, when we look at biological evolution as computer scientists, we can choose to view biological evolution as basically an algorithm. We see a population of organisms. Those organisms have genetic variation. Organisms that, partly because of their genetics, are less fit, they collect less food, they're unsuccessful in avoiding predators, and so on. They sort of die off. They have a better chance of dying off before producing offspring. Those that, again, partly due to their genetics, are more successful and live long enough to produce offspring. Those offspring obviously inherit some version of their parents' genes, which means they also have a chance of being more fit in their given environment. And repeating this process over and over again gives us a population of organisms that are fit relatively well to their ecological niche. That observation back in the 1960s actually led to what was known then as the genetic algorithm. This was a very, very early form of AI, which basically distilled biological evolution down into an AI algorithm where we replace our organisms with strings of numbers which are meant to represent candidate solutions to a given problem. So, in a genetic algorithm, we tend to start with a population of random solutions. So we generate vectors with random values in them. We take each candidate solution. We see how well it does at solving whatever problem we want it to solve. Those that do a poor job of solving the problem are deleted, which leaves some survivors, and the survivors are allowed to produce randomly modified copies of themselves. There are different ways we can make randomly modified copies. We can take a given solution, like this particular vector here, and make a copy of it. And as we're copying the numbers into an empty vector, every once in a while, when we copy that number, we alter the number a little bit. This is obviously meant to simulate biological mutation, genetic mutation. We can also take two surviving solutions, chop them in half, and take one half and combine it with the second half of the other solution and put them together, which you can see here. So this would be a simulation of genetic recombination of genetic material from two parents. Lots of different ways we can randomly modify surviving solutions. Okay. Back in the early 1990s, people took a genetic algorithm and combined it with robotics, where now the robot is viewed as a candidate solution to a given problem. We want the snow to be shoveled from our driveway. That's the problem. A candidate solution would be a wheeled robot. Another candidate solution would be a legged robot, and so on. So we're imagining a large number of robots, some of which are better at solving the problem than others. And we do the same thing. We generate a bunch of random robots to begin with. We see how well each one does at the problem. We delete the ones that are performing poorly and make randomly modified copies of the ones that survive. You've seen a few examples of this already. Here's an early example from some work I did a number of years ago now. This is a robot trying to solve a particular problem, which is to move along an aerial beam. And you can see in this case that it's evolved a solution to do so. It's not a perfect solution, but it manages to move along the beam somewhat. This behavior is known as brachiation, which primates are very good at doing, swinging from tree limb to tree limb. We are a primate species. We are not very good at brachiation. You can train, but you'll never be as good as a gibbon. I highly recommend getting on YouTube and checking out gibbons doing what gibbons do best, which is brachiating. You'll notice a couple things about the way this robot has evolved to solve this task. It's swinging this heavy weight at its bottom. These are meant to simulate the heavy battery packs that we had to use for the physical robot in this case. I mentioned last time when we talked about embodied cognition that the body is not an obstacle to behavior. It can often be exploited to facilitate that behavior. Here you can see another example of that. This robot has evolved the ability to use the momentum of the swinging weight to move itself forward along the beam. We took this particular evolved neural network, this set of synaptic weights that transforms the sensory values for this robot into motor actions. And again, it's not perfect, but does a pretty good job at solving the task. Yep. Okay, so we're going to spend a fair bit of time talking about how robots evolve in this course and evolving them to do a better job at the task. We're going to talk now about the fitness landscape, which is a metaphor that allows us to think about how evolution is proceeding or failing to proceed. The fitness landscape, this metaphor was articulated by an evolutionary biologist back in the 1930s, Sewell Wright. As the name implies, this is a hypothetical landscape. This landscape can exist in different dimensions. So we'll start in the upper left here by imagining a very simple fitness landscape that exists in just two dimensions here. You'll remember from a couple classes back, we talked about Bratenberg vehicles. And we started by talking about a very, very simple Bratenberg vehicle that had one temperature sensor on its front and one wheel on its back. And there was one synapse that connected that temperature sensor to the wheel. We can imagine setting different weights for that synapse that would cause the robot to move differently in the presence of different temperatures. And so we can imagine now doing a very, very simple evolutionary algorithm where we're going to evolve just that one synaptic weight to try and get the robot to move in a particular way whenever it's in warm or cold water. So we can think about a fitness landscape associated with that robot and that one synaptic weight by creating one horizontal dimension here that's going to represent the value of gene 1. There's only one gene for this robot, and that gene encodes a floating point value, the weight of that single synapse. We can then add a vertical axis here, which is fitness, and we can then imagine for any possible setting of the weight of that single synapse, we can ask how well the robot does at whatever we want it to do. For example, we want it to move at 3.2 meters per second when it's in cold water, and we want it to move 7.4 meters per second when it's in warm water. Doesn't really matter for our purposes what the desired behavior is, but for different settings of that synaptic weight, the robot is going to do more or less well at whatever it is we want it to do. And we remember we're always boiling that down to a single fitness value. Yeah, that's the vertical axis. So in this cartoon example here, whatever the value of this synaptic weight is, the robot is doing a poor job at that task. For this particular setting of the synaptic weight, the robot is doing a better job, but still not great. At this particular setting here, some synaptic weight that's kind of at a medium value, the robot does almost perfect at whatever it is we want the robot to do. Yep. Okay. Let's now imagine the second Bratenberg vehicle that we saw, the aggressor, that has two light sensors on its front, two wheels on the back, and it has contralateral connections. It's got two synapses. And imagine now that we want that robot to move towards the light and smash into it. We saw when we talked about Bratenberg vehicles that we can figure out what those weights should be. Imagine we don't know what those weights should be. We need to come up with two numbers to set those two synaptic weights and then measure how well the robot does at turning towards and smashing into the light. In that case, we can think about a fitness landscape that exists in three dimensions, where we have two horizontal dimensions now representing the weight of the first synapse, and the second horizontal axis representing the weight of the second synapse. And if we now think about that horizontal two-dimensional plane, any point in that horizontal two-dimensional plane represents a set of two coordinates and represents a set of two weights for those two synapses. As always, our third dimension, or our last dimension, is a vertical dimension fitness, which is how well the robot is doing at turning and smashing into the light. Yeah. And again, in this case, I just picked a cartoon 3D landscape here. And this would be, these are two simple examples here. In your case, you're going to be evolving robots that have dozens of synapses, which means in every case, for however many synapses you have, let's imagine you have n synapses in your neural network controller for your robot. You have a fitness landscape of n plus 1 dimensions. We have n horizontal dimensions corresponding to each of those synapses, and the n plus 1 dimension represents the fitness of that combination of synaptic weights. We're going to talk in this course about genotypes and phenotypes. A genotype, the genotype represents the storage of genetic information, the combination or collection of all of these synaptic weights. The phenotype is the thing that's produced by that genotype. In your case, it's going to be a robot and how it moves. A phenotype of an organism is the way that organism looks and the way that it acts. So the organism's form and function. Yeah. Okay. Throughout this course, you're going to be implementing a series of increasingly powerful evolutionary algorithms that do a better job of evolving your robot to do whatever it is we want that robot to do. You're going to start in assignment 6 by implementing the simplest evolutionary algorithm you can imagine. It's so simple, it's not really even an evolutionary algorithm, because there is not even a population of things that are evolving. There is just a single individual at any given time. So how does this work? Well, we start by creating our population. Our population at this point is a population of 1. We start by creating a single random solution. Here's the genotype here, which encodes all of the information. Again, I'm just showing this, I'm showing on the upper right here a very, very simplified version of the fitness landscape that corresponds to this cartoon example here. You can see that there are multiple genes here, but I'm assuming over here we have only one gene so that I can draw this fitness landscape in 2 dimensions. So we have a random set of genes, which means we land at some random horizontal position along this axis, which let's say is over here. We're going to refer to this individual as the parent. There's only one at the moment. We evaluate the fitness of this parent, and we then know the height of this point in the fitness landscape. As you can see, it gets a relatively low value. We want to obviously come up with a series of numbers that obtains a high fitness value. We can see the fitness landscape in this case, so why don't we simply travel to this point and set the gene value to this? Remember that for all the problems we're trying to solve, we can't actually see the fitness landscape. So imagine that our fitness landscape here is the Green Mountains, but it's completely covered in fog, and you are teleported to some point in the Green Mountains and you're surrounded by fog. How do you know how to proceed? How do you know how to move so that you climb up the Green Mountains? In the case of a hill climber, the hill climber starts by taking a step in a random direction. What does that mean? We take our parent, we make a copy of that parent, and when we make a copy, we make a random change to to the values of one of the genes, which means that this new point, this new child, has moved a small distance horizontally away from the parent. We evaluate the fitness of the child, and in this cartoon example here, the fitness of the child is slightly worse than the fitness of the parent. So you've taken a step in a random direction in dense fog on the slope of the Green Mountains, and in this cartoon example here, you've taken a step downward. What would you typically do? You'd probably stop and move back in the direction you just came from. It's exactly what a hill climber does. It deletes this child because it took a wrong step, and we make another randomly modified copy of the parent. We take another step in a different direction. In this case, imagine that this new child lands here. The child is actually better than the parent. You've taken a step in the right direction. The child is now higher, has a higher fitness than the parent. What do you imagine happens in the case of the hill climber at this point? The hill climber deletes the parent, and this new child becomes the new parent. Yeah. That's why this is called the hill climber. It randomly moves up the hill that it originally finds itself on. There's a problem with this, of course. In this cartoon example here, if you're moving in the fog and you're just following the local gradient, you're moving up and up and up, you'll eventually come to this point in the Green Mountains. Let's imagine this is Camel's Hump. It's pretty high, but it's not as high as Mount Mansfield. So at some point, you get to the top of a local peak, and you now cannot take a local step in any horizontal direction and make an improvement. You're stuck. You're stuck on what's known in evolutionary algorithms as a local optimum. In a local space, this local space here, this is the optimum. In this local space over here, this is the optimum. Unbeknownst to you, as the hill climber, you've missed the global optimum, which is up here. Yeah. So we can create increasingly complex evolutionary algorithms that decrease the probability that we're going to get stuck on local optima. The hill climber, as you can see, is very, very simple to implement. You're going to implement it in assignment 6. It has the benefit of being simple to implement, but it has the drawback in that it's very easy for it to get stuck on local solutions. It is not guaranteed, and it's very unlikely that any given run of the hill climber will find the best solution that's out there. So let's have a look at a slightly more complex evolutionary algorithm. This looks a little bit more like an evolutionary algorithm because now we actually have a population. At the beginning of this algorithm, we create a population of random vectors. We create a population of random genotypes. Let's say we have n parents. We have a population of n initially random solutions. In my cartoon example over here, we're going to set n equals to 2. So we have parent 1 and parent 2. We've initialized all the gene values with random values, which means P1 and P2 falls, each of them falls at random horizontal positions in this fitness landscape. We compute the fitness of these. P1's a little bit better than P2. And then in parallel, each parent produces one child. And like in the serial hill climber that we just saw, if the child's fitness is better than the parent, we delete the parent and the child becomes the new parent. If the child's fitness is worse than the parent, the child is deleted and the parent produces a new child. Again, I've kind of cooked this example over here to show that still the parallel hill climber doesn't perform great because it's still searching locally. And in this case, you'll notice that this particular parent 1 and its offspring are eventually going to get stuck on this local optimum. And parent 2 and its offspring are eventually going to get stuck at this optimum. So let's keep going. Beyond this is the genetic algorithm. This is something you're going to implement in one of the later assignments. I don't remember exactly which one. This incorporates a particular biological detail, which is genetic recombination. And genetic recombination in the genetic algorithm, like in nature, its advantage is that every once in a while, genetic recombination combines the best of both worlds. It happens by chance to combine good genetic material from one parent with good genetic material from a second parent. How does this work? Well, the genetic algorithm starts like the parallel hill climber. We create a population of n random vectors, n random genotypes. Each genotype has a random setting for each of the genes. And in our cartoon example, again, P1 happens to fall over here, P2 happens to fall over here. When we produce offspring, we're now not going to produce offspring from individual parents, but combined parents in the following way. We have the red parent here and the blue parent here. We choose a particular point in both parents and cut both parents at exactly that point. And we take all the numbers to the left of that cut point from parent one, from the red parent, and copy those values into our first child. And we take all values to the right of that cut point from parent 2, from the blue parent, and copy that into child 1. So child 1 contains some genetic material from parent 1 and some genetic material from parent 2. Child 2 is the opposite. We take the right-hand material from parent 1 and the left-hand material from parent 2 and put that in the second child. So we're recombining genetic material in different ways from these two parents. In our cartoon example here, child 2 was unlucky. It somehow got genetic information that left it stuck on a local optimum. But for some reason, just by chance, there was something about the left-hand values in parent 1 and the right-hand values of parent 2 that were partially solving the problem. But when we brought them together, they're collectively solving the problem better, which is represented in our cartoon example here by C1 landing on the slope of Mount Mansfield. It's on its way to the global optimum. It doesn't know that. It just knows that it has a fitness better than both parents and its sibling over here. I'm going to jump back and forth between the cartoons on these two slides. You'll notice another difference of the genetic algorithm compared to the parallel hill climber is that C1 and C2 are a further distance horizontally from their two parents. This is because the children are numerically more distant from the genotype of any one parent, right? Before we were in the parallel hill climber, we were changing one or maybe a couple of numbers in the child. So the child genotype was much more similar to its parent's genotype than in the case of the genetic algorithm, which means the children can move further horizontally, which means they can move out of local basins that are trapped in a local optimum and can land in new space and can invade new spaces in the fitness landscape, which might lead to better and better solutions. Yeah, you sort of get out of a genetic rut, and it's possible that children in this way can innovate, evolutionarily innovate. Okay. Let's keep going. Genetic algorithms also still have a problem. They can also get stuck in certain ways. How can they get stuck? Let's have a look at an example here. Let's look at an individual genotype here, represented by this point. And we can think about, let's forget about the genetic algorithm for a moment. Let's go back to the hill climber and imagine that this individual parent is going to produce a child. We're going to take all the values in the genotype of the parent and copy them into the genotype of the child. When we change a value, we're going to randomly change one of the genes. We're going to randomly mutate one of the genes. We're going to mutate it by a certain magnitude. We're going to change the value of that gene by a certain amount. Imagine that we're going to change it only up to and including a 0.1 away from the original value. That's known as the step size here. We're basically setting the allowed magnitude of the mutation. How far from the parent can the child be? If we have just one gene, and here's our parent here, that means the child can be up to zero 0.1 units to the right of the parent or 0.1 units to the left of the parent, yeah, represented by these thin lines here. In this example here, unbeknownst to us, a step size of 0.1 was actually a pretty good choice, because if the step size is 0.1, we have a 50%, the child has a 50% chance of being better than the parent, as long as the mutation decreased the value of gene 1, meaning that as long as the child is to the left of parent 1, it's actually going to land higher up the slope of Mount Mansfield here. So that's pretty good. Imagine, however, we have this particular parent here, and the fitness landscape looks like this. If we imagine again a step size of 0.1, you can see that if the child is mutated, if the value of gene 1 in the child is mutated in this direction, it's going to end up being lower than the parent. And 0.1 to the left of this parent, also most of those mutations are going to cause the child to have a lower fitness than the parent. There's only a very narrow range here in which the solutions would be better. So it would be great for this particular parent if it had a step size that was smaller. So imagine the step size was, whatever this is, 0.3. Then anything to the right up to 0.3 would still be worse than the parent, but anything to the left would be better than the parent. So we'd again increase the chance that the child would be better than the parent. What I want to communicate with these two cartoons is that the step size we choose, the magnitude of mutation, influences how quickly or how slowly children improve upon their parents. Remember that we don't know what the fitness landscape looks like beforehand, so it's very difficult to know what the step size should be. And it might be that the step size should be a particular step size in particular parts of the space, and the step size should be different in other parts of the space. So there is another evolutionary algorithm known as the evolution strategy, in which we have our N genes that represent a candidate solution to the problem. And each gene has associated with it a step size. So the genotype, which is now the encoding of the problem, is no longer a 1 by n vector, it's a 2 by n matrix. Yeah. So whenever a particular genotype is copied and mutated, so like this parent here, we might copy it and mutate. Let's say we choose by chance this particular gene to mutate. We're going to mutate it by this magnitude. So we're going to replace the 4 with any new random value between 0.2 and 0.6. If we had chosen this gene over here for mutation, we would replace this value 0.7 with any value between 0.65 and 0.75. Hopefully most of you are wondering, how did we get these values in the first place? These values themselves also mutate and evolve over time, so that as these points travel through the fitness landscape, they evolve step sizes that tunes the distance they move. Whenever they take a step in a horizontal direction, that step is calibrated. The magnitude of that step is calibrated through evolution, so that the children are more likely to be more fit than the parents. For some of you, hopefully you now have a second question in your mind, which is, how do you know how much to mutate the step sizes by? There's also a way to determine that, but that's beyond the scope of this course. Again, what I hope you take away from this this lecture series is we're seeing a bunch of more sophisticated evolutionary algorithms that become more and more complicated. But that complexity is valuable because it increases the chance that when we run this evolutionary algorithm, it's going to discover and start to climb the slopes towards globally optimal solutions and avoid getting trapped in locally optimal solutions. We're going to look at one last evolutionary algorithm now, which is interesting for a lot of reasons. One of them is the way in which the genotype is encoded. We just looked at some evolutionary algorithms in which the genotype is encoded as a vector or a matrix. In this evolutionary algorithm, the genotype is encoded in a different way. Before we introduce that evolutionary algorithm, let's introduce a particular problem that this evolutionary algorithm is good at solving, called symbolic regression. Let's imagine that you're a scientist and you collect some data that looks like this. You have your independent variable here, x, and for a bunch of values of x, you take a measurement and you get back values for your dependent variable y as follows. And just when you plot the data, you notice that there seems to be some relationship between x and y. It's not a straightforward relationship, but there is a relationship there. And you'd like to actually write down an equation that describes y as a function of x. Some of you may remember this from high school algebra, high school math classes where you had to actually do this kind of by hand. If we were doing this lecture in person, I'd ask for some guesses. Here's a bad guess. We might start by guessing y equals x, which is represented, that relationship is represented by the thick black line here. You'll notice that this thick black line is a long distance away from most of your actual data. So I've represented the error here by the thin vertical lines. I haven't drawn all of them here. So this particular equation gets high error, which we can think of as low fitness. This particular equation here actually gets low error. So here's y equals x minus 3 squared. Again, I've tried to draw, I've drawn some of the errors here as vertical lines. It's not zero error, but it's a lot better. This particular equation gets higher fitness because it has lower error. So imagine now, instead of trying to do this by hand, which as you probably remember from high school is a difficult thing to do, we can automate this process by evolving populations of equations, and for each equation, measuring its error and turning that into a fitness. We can delete the equations that have low fitness or high error, and make randomly modified copies of the surviving equations until we obtain an equation that describes our data very well. That evolutionary algorithm is known as genetic programming, and we'll talk about genetic programming in a moment. Let's motivate this a little bit more by taking a real local example. If you've ever spent any time here in Burlington in the summer, Lake Champlain's a great place to hang out. But every once in a while, the lake suffers from toxic algal blooms. They're really bad for dogs, and not so good for humans either. It's difficult to actually predict where and when and how intense an algal bloom will form. So there have been a number of research projects here at UVM over the years to collect data and actually try and learn a relationship between different features of the lake, like the amount of nitrogen in the water, the amount of phosphorus in the water, its temperature, turbidity, how clear the water is, the amount of rainfall, and so on, and use that to predict whether or not an algal bloom will appear at that place and at that time in the lake in the not too distant future. Yeah. So here are all our independent variables, and here's our dependent variable over here. Yeah. Turns out that T equals N or T equals P are pretty good. Nitrogen and phosphorus runoff from farms surrounding the lake definitely influence toxic algae. But N and P alone are not good descriptors. There are relationships between N and P, combinations of N and P that predict better, that also depend on water temperature, turbidity, rainfall, and so on. So this is a real problem. It would be great to be able to actually generate an equation or a predictive model that tells us when an algal bloom is likely. Okay, so let's look at genetic programming, which, as I mentioned, is a way to solve a symbolic regression. We'll also see some evolved robots that use genetic programming to evolve behaviors for them. We'll see that later in the class. But let's focus on genetic programming for symbolic regression at the moment. Here's one individual in a genetic programming population. Here's a second individual in a genetic programming population. You'll notice these are neither vectors nor matrices. They're represented as trees, and these trees are encoding equations. How do they encode equations? Well, let's back up a moment. Let's assume that we haven't created these random trees yet. We're going to start with P1 and we want to create a random equation. We actually want to create a population of random equations and then evolve them to have lower and lower error. So how do we create a random equation? We're going to start with P1. We start by defining all of the possible mathematical operations that we think could be useful. And we also define, or we define all the state variables, the things that we can actually measure about our problem, X, Y, Z, excuse me, or N, P, W, B, R, and so on. And we also throw in some random floating point values that can be incorporated into our equation. Okay, so we start with P1 by putting all of these operations and operands into a bag. We shake up that bag, we reach into the bag, and we pull something out at random. In this example here, we pull out multiplication. So we stick that as the root of our tree here. Multiplication requires two arguments, two things that we want to multiply together. So we create two empty nodes underneath the multiplication. We have an empty node here. So we go back to our bag of operations and operators. We shake it up again. We reach into the bag and we pull something else out. In this case, we've pulled out addition. Addition also requires two arguments. So underneath the addition sign, we create two more empty circles. We reach back into, we shake up our bag, we reach in again, we pull something out. In this case, instead of grabbing an operation, we grabbed an operand. In this case, we grabbed a random floating point value. We stick that in. We still have an empty circle here. Reach into the bag again. In this case, we pulled out one of our independent variables, X. And remember, we filled in everything here, but we still have one remaining empty circle over here. Reach into our bag again, and in this case, we happen to pull out a random floating point value. Whenever we grab from the bag an operand, like a state variable or a random float, those don't require any arguments, so we're kind of done at that point. So far, so good. I forgot to mention with our bag, this is selection with replacement, meaning once we grab multiplication, we throw it back in the bag, and multiplication has a chance of being grabbed the next time around. Okay, so we've created one random equation over here. P2, we're going to do the same thing. We reach into the bag a bunch of times, and we end up creating this tree. So we have a tree. A tree is representing our genotype. This is our genotype 1, genotype 2. It's hard to read this as an equation, but you can do so by descending this tree. And we're going to descend this tree in breadth first manner, meaning we're going to start up here. We're going to hit multiply first, then plus, then 8, then x, and then 1.4. When we do, that causes us to write the following. We write the multiplication, and now on either side of the multiplication, we need to write something. On the left side of the multiplication, we come down here, we place a plus here. We need to write something on either side of the plus. We visit point 8, put that to the left of the plus. Come down here, put the x to the right of the plus, and we repeat this process and we get this equation. Same thing over here. We descend this tree, and as we do, we write things out to the left and the right of whatever we wrote previously, and we get something that looks more familiar. This is just for us. The genetic programming doesn't actually do this. Genetic programming just maintains a population of trees. Okay. Returning to our example of toxic algal blooms, let's imagine that this particular equation is not very predictive of algal blooms. Or I'm sorry, I misspoke. Let's assume that this is relatively good at predicting algal blooms, and this solution is also relatively good at predicting algal blooms. There were some other, let's imagine we created P3, P4, P5, and so on. Some of those were not very good at predicting algal blooms. Those particular genotypes, those particular trees were deleted, and these are the survivors. We need to make randomly modified copies of these survivors. We could do so through mutation, like we saw before. We could take P1 and make a copy of this tree. This could become C1 over here. And we could then pick some random node in this tree, delete what's inside that node, and reach back into our bag and pull something else out and put it into that node. So we make a local change to the copied tree. We could also recombine genetic material from two parents in the following way. We have P1 and P2 over here. We're going to create two children, C1 and C2 over here. Like before, we're going to take these two trees and we're going to cut them at certain points. We're going to cut P, and we can choose these points at random. We're cutting P1. We choose, in this case, to cut P1 at this point. And in P2, we choose to cut P2 at this point. We then we pull off of these two parents the subtrees that are to the right side of the cut point. So I pulled off point 1, and I've pulled off x plus y. And we swap them. So in C1 over here, C1 inherits this genetic material from P1, but it's going to then inherit this genetic material from P2. And C2 inherits this genetic material from P1 and from P2, and it's going to inherit this genetic material from P1. Yeah, we've swapped this genetic material. Okay, you can imagine continuing this process. We have a population of these trees. We're deleting some of the trees and make randomly modified copies, or we combine material from different trees to try and evolve equations that better and better predict T from these variables by combining these variables in different ways. That's using genetic programming, a type of evolutionary algorithm to solve a particular problem, which is symbolic regression. You can also use genetic programming to solve other kinds of problems. Any problem where you can encode candidate solutions in a tree is amenable to genetic programming. So we've got 1 minute left. We'll finish with kind of a fun example. In this case, we're going to evolve trees, and those trees generate images, like you can see over here. And the fitness of an image is how well it approximates a particular image. Hopefully you all recognize what this image is over here. So to finish up, actually, I'll speed this up a little bit. You're watching this evolutionary process. You can see the generations counting off at the top of this figure. And you can see, hopefully you can start to see how different trees in the population are creating different images. And these images slowly and slowly are getting better at approximating the Mona Lisa. As a thought experiment between now and our next lecture, I want you to think about how is it that the tree is encoding these figures? So we're going from a tree to a PNG, to an image, and then we're taking that evolved PNG and comparing it against the PNG of the Mona Lisa. And the difference between those pixel values represents the fitness of the tree, the genotype. So again, just to practice some of our new terminology. The genotype is the tree. It's the encoding of the candidate solution. And the phenotype is the thing produced by the genotype. In this case, the phenotype is an image. In symbolic regression, the phenotype is the equation itself. Again, thank you for your patience today. I apologize for my voice. You have a quiz due tonight. Undergraduates, you're working on assignment 3 now. Graduate students, you're working on assignment 5 and 6. I'll be sending around an email tomorrow about what form class we'll take on Thursday. Thank you. Bye-bye.